Time to start. Welcome everyone to the third direct write lithography workshop and its webinar series. Today we'll finish off with webinar number 7. Before we start, I'd like to do a few acknowledgements as always. First, I'd like to recognize the traditional owners of the country which we gathered here today, which in my case is the people of the Kulin Nations. And I pay my respects to their elders past and present. Furthermore, I'd like to acknowledge the Australian National Fabrication Facility for their ongoing support, and especially its CEO, Jane Fitzpatrick. And of course, the whole team for helping to putting this webinar series and workshop together. Of course, this workshop and the webinar series would not have been possible without the sponsors. So a big thank you to all of them for their ongoing support. And of course, our sister meetings, conferences, and workshop, Mabel, the 3BIMS meeting, EIPBN, and Thermal Probe workshop. As mentioned previously, we'll also run a Mabel X meeting, which is hosted well, within Australia or from Australia, early August. And well, this brings me to the last webinar, Contrast Curve Basics and Applications to Understanding Resist Development by Leonidas Ocola. Short bio, very short. Leonidas is with IBM since 2017. Before, he was a member of the University of Chicago. He did his PhD in physics, at the University of Wisconsin-Madison in 1996. He has many awards and honors, such as he's a fellow of the American Vacuum Society. Also, he was the conference chair for the 3BIMS meeting, the 57th in 2013. And quick research areas. Leonidas' research interests include electron beam lithography, simulating high energy electron beam interactions with polymer materials, scanning probe characterization techniques, FTIR, microspectroscopy, single molecule spectroscopy, nanofabrication, metal oxide devices, ALD infiltration and nanostructured polymers, and the properties of such modified materials. I also like to mention that when we thought about this webinar series, Leonidas and Scott, those were the two names which came to our minds the first. So we're very happy to have him again for webinar number 7. And yeah, well, Leonidas, the stage is yours. Please, let me stop share my screen. And please share your screen. And we're looking forward to your webinar.
Yeah, thank you, Michael, for the kind introduction. And hope you see my screen.
Yes, we can.
Okay, great. So yeah, before I start, I wanted to apologize for the previous talk. It was maybe too many overheads and a lot of information. I didn't spend enough time maybe in each one of them. So I'm gonna try to go a little slower this time. So the talk is on contrast curve basics and how you can use this for understanding how resists work. So let's see the first. Okay, so contrast curve is the most basic thing you use to understand how a resist responds to any radiation. If it's optical lithography or even lithography, it's just a series of pads that you expose them with increasing dose, and then you put it in the developer and you measure the thickness change in the exposed region. Okay, if it's a positive resist, then there will be thickness loss as the dose increases, and this is an image for a positive resist. If it's a negative resist, the thickness, there will be nothing there until it starts to show up little by little, until it becomes a very nice solid region. Okay. And so this is used to basically determine where does the resist clear or where does it start to it's a positive resist, or where does it start to form? It's a negative resist. And there's also the concept of contrast. And I'm actually going to challenge that concept because I think, in a way, it's been like I say, it is importance has been overstated because it's, and we'll see what I mean. So the basic definition of contrast. Let's segue to that. You can look at the literature and go back. And so these are the two classic examples I found. The literature, one by Gary Bernstein and Mr. Brunner. And basically, you say, all right, we're going to try to get the slope out of the curve. And you will define then, pick a threshold dose on the upper end of this resistance, positive resist, and then the other end, and voila, you get the contrast. And the idea was, okay, it's a way of determining how fast does an image get resolved with dose. So if this was just a mathematical delta function, it'd be great because it's there, not there. You get really high resolution patterning. Reality, it's never straight down. But and on the right hand side is more or less the same thing, but they're looking at more of a definition based on derivative of the log. No, this is the log plot and dose. And well, the problem is that the data that you collect when you're trying to collect these thickness changes is never so clean. It is never this beautifully placed. There's going to be noise, and then you have to ask yourself, well, which data points do I pick to select this slope? And it's a log slope is very sensitive to any experimental noise that you have. And I'll show you what I mean with that. So yeah, it never looks this nice. So here's some real data on a PMMA and MMA. And so you have little fluctuations. So I came up with something, an empirical formula at the time. It was about 9 years ago, where this had to do with, okay, this looked like an exponential, and I used this formula, and it's just a constant. So this is basically 1 or almost 1. And I used the Brunner's definition of the derivative. But when you have a formula, now you will smooth out any experimental noise. And you got, even though it's not very clear here, you got 3 curves. This is the MMA as a function of dose, which is a positive resist. It'll disappear if you expose too much. Then you got PMMA, which is the triangles. And you got Caesar, which is like ZEP. If anybody used ZEP, that's this. And you'll also have these other secondary things, which are basically the foot. So these resists are not ideal, and since it doesn't go straight down with this formula, there is foot, and this is just something else going on in these type of resists that I can explain later on. But the bottom line is that I started looking at this and just empirically said, oh, this looks like a great fit, and I can use then this stuff. And then by definition, if you take the derivative of this and you evaluate at the dose to clear, so D becomes equal to the dose to clear, which is the dose here, which reaches 0, your contrast comes out. So the contrast is actually the product of the parameter that defines how steep this is, which we're going to see relates to the dissolution rate, and the dose to clear. Now, if you ever have looked into literature of different contrasts for different resists, you may start noticing that the very insensitive resists, especially positive resists, the insensitive resists, they have higher contrast, always. And the resists that are very sensitive will have very low contrast. And it's just because the dose to clear is a part of the factor. It doesn't matter how sharp you are. If this gets if the DC gets lower, then the overall contrast goes down. So that's why, and I'll show this is not really an inherent property of the resist. It looks like it by the definitions that we've seen before, but in reality, it's not. The inherent properties of the resist are going to be the dose to clear or the dose where the negative resist starts to form. and this parameter, which is going to be, I'm going to show, is related to dissolution rate. Those are inherent properties of the resist. So let's move on to the next one. So it turns out that a while back I was looking at I showed this in my previous talk about the soluble site density, and there was this paper showing the protected sites as a function in density and the dissolution rate. And it turns out that I noticed that I could fit this to a simple exponential. And so it turns out that this works for both positive and negative resist, because you go up. If you increase the density of soluble sites, then your dissolution rate goes up. And if you're taking away soluble sites, your dissolution rate goes down, which is a negative resist. So it turns out that say, oh, this may relate to my formula. And so I was looking at here a separate paper just to make sure that I'm not delusioning myself that, yeah, this is maybe it was coincidence, a fluke for the one paper. This is a separate independent paper. I got their data. I fit it to an exponential, and this is the dissolution rate. It's a function of dose. So you can actually relate the dissolution rate with dose, which is it's a little bit different than density of soluble sites. This is actually now a more common number that we see all the time, dose. So we could tie these these concepts up by just doing a little bit of math. So if the dissolution rate follows this formula, which is, we saw it was associated with the density of soluble sites. Okay, when you calculate the remaining resist thickness, it's going to be the initial thickness minus, and then the integral over time of the dissolution rate, right? And so when you normalize, it means you divide by the initial thickness, you get this formula. And then you say, well, we know that the density of soluble sites is proportional to the dose. It's just, right, on the more dose I throw in, the more deprotection sites I'm going to create. It's all linear. So I have basically a scaling factor. If you replace that now in the formula, now you have an expression where you have a dose. And you just carry out this integral, which, yeah, I had to look it up. It's been like, I don't know, 40, 50 years since I've done integral. So yeah, I got it done. You see here now this function, and it's starting to look like the formula I had. So the boundary condition is, right, that at the dose to clear, and this is a positive resist or even a negative, so that particular dose where things show up, the thickness is 0, right? So I have a boundary condition. So I put that 0, and so I can express the thickness as a function of the expression that was describing the dissolution rate and using now the dose to clear. So I can insert that back into the formula, and voila, I get my formula that I had in a couple overheads before. And so this parameter S is basically the product that is defining the dissolution rate here and associating the density of soluble sites with the dose. Okay, so these are inherent properties of the resist. Okay, and so that's where this comes from. Then this is just, and the funny thing is that there's somebody who's published papers on these things, and their formulas are completely different than mine. And I've actually asked a colleague and tried to compare these two papers, and he's like, "You're both right." So I don't know. But it'd be interesting to see if somebody can also look into this, and maybe there's something that can be expanded. But this is very interesting. Is that now we can give a physical meaning to contrast, but we're going to show that these are the properties that you want to optimize for a resist, and I'm going to show how they're used to optimize the performance of resist. I had said that this works for negative resistance, so here's the proof. This is data that I took for a negative resist, and these are not two different resists. It's just that This is a negative chemically amplified resist where on the one side, I did not do any post-exposure bake and it still behaves negative. And on the other side, I did do a post-exposure bake. So this is interesting. You really can play with resists if you play with their post-exposure bake temperature and time. And really, you see here, the sensitivity is over an order of magnitude change. And you will buy yourself some benefits in certain things and maybe a compromise in others. For sure, you will lose sensitivity when you'll lose resolution when your resist is more sensitive. But your exposure time will go a lot higher if you are going to this higher resolution regime. So it all depends what you need your resist to do. Okay, so quickly, one of the things that I like to do, and I recommend people to do when they're doing contrast curves, is don't do a brute force linear bin of doses. So don't measure every 10 microcoulomb, because then you're going from let's say this regime to 1,000. It's going to take you forever in terms of data. So I use a factor, or basically a product. It's not a linear scale. The bins increase by a factor each time, get larger and larger and larger. And so when you plot in a log plot, it looks like they're equispaced between them. And the reason is that basically this property of the resist is scales with the log plot. So you want to bin it in a similar fashion. And so the way that I do it is I create a pattern that just has 10 boxes, 20 boxes with different that are spaced far enough so I don't have any interaction between the boxes when I expose. But the factor is basically, here's the multiplier. It's a weird number, 1.0888 something something. And the only reason was I fiddle with it so that as I multiply it, I go from 1 to 5 between the first dose and the 20th dose. And so it's easy because now I know that I have in 20 pads, I have covered a factor of 5 in dose. And when you're doing E-beam, your pattern, if your pattern has these dose multipliers in your pattern, and you're defining a base dose, then you can expose with different base doses and actually very quickly. You see here with two sets of these, so this is 40 patterns. I go from 100 to 1,000 very quickly. And actually you like to have a little bit of an overlap so you have some extra sampling between these two groups. And so you collect data of these two groups and you plot them, and you can actually see, I'm not sure if you guys can see that, but in this region here you have the oversampling. And so it tells me that, yeah, I got a nice curve and my data helps with the fitting too. And so this is an example of how you can implement this pretty quickly. This is just an Excel spreadsheet, which now is my extent of mathematics and simulation, just Excel. But yes, so this is just zooming in so you guys can see what we're talking about, this 1.08. It was just to go 1 to 5 within 20 steps. And then it's easy to do this. In reality, for me, what I do I have one pattern, basically 4 of these arrays that I do, and I can cover from 40 microcoulomb to 4,000 microcoulomb very quickly. And I can easily then evaluate any resist with my tool in one shot, in one exposure. So yeah, I'm gonna skip this because it's basically the same thing what I talked about. And the fitting is just with Excel you can put in your parameters for the thickness, initial thickness, that S parameter, the dose to clear, your constant. From here you can calculate then what the contrast is, the gamma, and this is just for me so I can calculate more or less